Good afternoon, friends. This is class of BSc third semester for the academic year 2020-21, and I am going to teach you for this semester electrostatics. In electrostatics, particularly you are studying dielectrics. The use of dielectrics, its importance and its application. So, the introduction of this topic, let me start with this. Substances like glass, ebonite, mica, say air, are called as insulators. Insulators, also known as, say, dielectrics. These insulators or dielectrics plays the important role. You all know the basic principle of capacitor. Capacitor has two plates in it, parallel plate like this. One is a positively charged plate, other one is a negatively charged plate. This is positively charged plate and say this is negatively charged plate. In between there is a gap. Now, capacitor, the basic purpose, basic principle of a capacitor is to store the charges. Now, the storing capacity, that is called as capacity of a capacitor, will be enhanced when we insert a material called as a dielectric material between these two plates. Without dielectric material, a capacitor will have a different capacity. When we insert a dielectric material called as insulator, its capacity enhances. That means capacitor is widely used in electronics, electricity. So its importance here basically to enhance the capacity of a capacitor. This is true not only in case of parallel plate capacitor. This is parallel plate capacitor. It is true for other capacitors like cylindrical capacitor, spherical capacitor and so on. So, importance of called as insulators or dielectrics. Dielectrics are also known as insulators, or insulators are also called as dielectrics. But dielectrics plays very important role in electricity as well as in electronics. We'll see the basic things. We all know matter, as we all know, it is having four states: solid, liquid, gaseous and plasma. Matter is made up of molecules. In turn, molecules have one or two atoms. We know atom as a whole is a neutral. Atom consists of a positively charged core called as nucleus, and around the nucleus electrons are revolving in circular or circular-like orbits. Electrons are negatively charged particles and nucleus is a positively charged core. So overall, the atom, when it is in its ground state, it is neutral. Atom as a whole is neutral. Atom as whole is neutral. But in solids, if you take an example of solid, so atoms are very closely placed in solid. Their interatomic distance is very small. It's very small. It is in the order of 10 raised to minus 20 meter. So they are having interatomic forces, intermolecular distance or interatomic distances, and they exert a force. They exert a force called as interatomic force. And because of the interatomic forces, see, the molecules are closely packed. Not only that, they exert interatomic forces, and due to these forces, some of the electrons, they get displaced, they get free. Means some electrons will become free from the atom. The free electrons, they move here and there. They move within the boundary of the material. So when these free electrons, when they interact with other atoms, either they will create a new electron and that becomes donating electron, atom become a positive ion, or vice versa here. So we get the atoms and then electrons in a solid here. The question here is, atom has a nucleus which is having a positive charge plus Ze, and there is a cloud-like situation very close, and these electrons, they revolve around the circular like orbits. We call this as a cloud. Now, these electrons which are revolving around the nucleus, they have the radius in the order of 10 raised to minus 10 meter. The point here is, the electrons which are revolving around the nucleus in different orbit, electrons which are close to the nucleus, they are said to be tightly bound with the nucleus, and the electrons which are in the outer orbit, say here, they are loosely bound with this parent atom. When this loosely bound electron, say, is close to another atom, there is force of the intermolecular distance is very small. There is a force exerting on this. So due to this, some electrons, they gets free, and those electrons, we call them as free electrons, and they move here and there randomly inside the solid here, and they are called as free electrons. Now, based on the behavior of these free electrons, we further classify the materials into three types. One we call here as conductor. The other one we call it as bad conductors or insulators. And third one we are calling it as semiconductor. Let us say about the conductors. You have studied this to have the idea what the role this dielectrics plays Dielectrics are also known as insulators. We are trying to know this. In conductor, so there are some good conductors, for example, silver, say copper, say aluminum. All these are good conductors of electricity. It conducts electricity. The conductivity of this materials depends upon the number of electrons, that is free electrons. On an average, one atom, at least on an average you can say it will have one electron free. In 1 cubic centimeter, say this per unit volume, almost the number of atoms we have 10 to the power 22. That is number of atoms. When we have this number of atoms, the number of electrons, free electrons, will be almost the same number. On an average, we are saying one atom will have one free electron. We are saying in general. So, if you take the volume, that is per cubic centimeter, so many atoms, that is in the order of 10 raised to 22. So 10 raised to 22 will be the electrons, and these electrons will be free electrons. The free electrons in conductors, they are moving here and there within the boundary limit of within the surface of the solid here. So we classify the materials depending upon the behavior of free electrons. We are concentrating more on insulators. Insulators are also known as dielectrics. In case of insulator, whether it is solid, say liquid or a gas, the number of electrons or the electrons are tightly bound. Almost no electron is free here. The electrons are tightly bound with the parent atoms and no electron is free here. You can say the free electrons in case of insulators or a bad conductors are, we call here it as a dielectrics, no free electrons. That means the conductivity in case of conductors, the conductivity is in the order of 10 raised to 20 to here electrons per cubic centimeter here, and for insulators no free electrons, and its conductivity is in the range, or it is in the order of 10 raised to minus 20. Now, if you look at the materials like solid, liquid and gases, in case of liquids, the interatomic distance is larger in case of liquids, and it is 10 times more, approximately you can say 10 times more than the solid materials. As a result, because of the interatomic distances are more in case of liquids, so some materials, they have no free electrons, and sometimes the liquids are also insulators. If you take an example of gas, the interatomic distance in case of gases is again more than that of liquid, and that much more than the solid. So because the interatomic distance is more in case of gases compared to the liquid and compared to the gases, some gases here no free electrons in case of gases, and therefore some gases are also they work as insulators, bad conductors as well. We call here as dielectrics. Well, broadly we have classified the materials based on their behavior of free electrons in solid, in liquid and gases. We have other class of materials called as semiconductors. The conductivity in case of semiconductor, it is not too high as like in solids or conductors, or it is not too low as in case of insulators. It is almost zero here in case of insulators. Intermediate or moderate conductivity, the semiconductors in general they have the moderate conductivity and their behavior depends upon the temperature. Semiconductors are very sensitive to temperature. So here in case of insulators, what is the importance of these insulators? What is called as dielectrics. I will give an example here. Say high tension transmission wires, power transmission wires are passed from one place to another, from pole to pole. They have been insulated by air. As I mentioned here, gases are also insulators. So the materials like glass, ebonite, say mica, say air. Air is an insulator. So while transmitting power, high tension, through high tension wires, you can say that's called as transmission lines. Power is transmitted through wires, you can say, and they are insulated. It is easy to transmit a wire, means transmit a power through cables or wires called as transmission lines. And these transmitting lines or a wire is insulated by air, and it will be easy for us to transmit the line. We have observed this in our day-to-day life. Well, in transformer, see this, a transformer is dipped into a insulating oil or called as liquid, which is also a dielectric. The transformers are dipped, or say a DC or AC motors or a small transformer called it a step down transformer. Initially it is dipped into a liquid, insulating liquid, to avoid why it is insulated means why it is dipped into the liquid to avoid what is called as leakage of currents due to say short circuiting or so. We have observed in electric poles, the electric wires which are open live wires, they have been clamped by porcelain material, which is a non-conductor here, that is insulator. There are many examples you can see where we have used insulators or dielectrics. Insulators or dielectrics plays a crucial role in electricity as well as in electronics. So let us come to the another point, what is called as this dielectric materials depending on dielectric substances, say for example glass, ebonite, mica, air. These materials are classified into two types called as non polar molecules. This is one type. The other type is polar molecules. It is polar and non-polar molecules. As I have drawn here, say in case of atom as a whole is neutral. Say it is having nucleus is having a positive charge and it is Z times E is the electronic charge and Z is the atomic number. Around this nucleus we have cloud-like picture or a situation. We know that electrons are revolving around the nucleus in circular like orbits, and we have studied this. We know about the distribution of electrons in different cells. We take this is for a different purpose. Outside the nucleus we have cloud-like picture, and this cloud-like picture is having, say, a negative charge. Z E is the electron charge and Z is the atomic number here. Now the point here is this electron cloud or a cloud-like picture. This is a layer, you can say. It is having certain radius and we have seen it. So this will have a center of gravity. The nucleus is positively charged and it is having the center of gravity. If I draw another picture here, the center of gravity of a nucleus, that is denoted by plus, and the center of gravity of electrons here in molecules called as non-polar molecules, or the non-polar molecules are the molecules in which center of gravity of a nucleus coincide with the center of gravity of electron or an electron cloud here. When both the center of gravity, that is a negative charge, and the positive charge, center of gravity of a negative charge called as charge of nucleus, and the negative charge is the center of gravity of here electrons. When they coincide at the center, one is overlapping the other. This is the picture, you can say it's a picture of or an atom of non-polar molecules. There is no distance between. Here atom as a whole is neutral. One charge we call it as plus Ze. The other charge is minus Ze. If this is, say, we take it as charge Q and say this is charge minus Q. If these two charges are separated by a certain distance of same magnitude of a positive charge is plus Q and magnitude of negative charge is, say, Q itself. If they are separated by a certain distance, that constitutes a dipole. Here, in case of non-polar molecules, the dipole moment is zero. Dipole moment is zero. What is the dipole moment? That is Q into D or Q into L. Q is the magnitude of either charge into L, the distance between the two charges. The product is called as dipole moment, Coulomb into meter. So, in case of non-polar molecules, the center of gravity of a positive charge is coinciding with the center of gravity of the negative charge, and when this is happens here, that molecule is having dipole moment, and the dipole moment is zero, and such molecules are known as non-polar molecules. The examples of non-polar molecules here. The non-polar molecules will not have any dipole moment. Dipole moment in a non-polar molecule is zero. Examples. The common examples of non-polar molecules, say it is hydrogen, oxygen, say nitrogen, say carbon dioxide, say carbon tetrachloride CCl4 and CH4 are some familiar examples of non-polar molecules. We'll go for a polar molecules. In polar molecules, the situation will be different. I'll draw a picture here for a polar molecules. In case of polar molecule, say the center of gravity of positive charge. This is the situation. This is positive charge and this is negative charge. Center of gravity of a positive charge is separated from the center of gravity of a negative charge. There is definite or a finite distance between the center of gravity of a positive charge and negative charge. Say this distance is d and say the charge is Ze, Z minus Ze plus Ze in case of polar molecules. So polar molecules are the molecules in which the center of gravity of a positive charge, that is a nucleus, and a negative charge called as electron or electron cloud is not coinciding, but they are separated by a finite distance, and these molecules, they have a dipole moment. As I said here, if this is positive charge is indicated by plus q and say negative charge is minus q and say d is the distance between them. So the dipole moment for polar molecule is q times d. In other words, we can say polar molecules are the molecules which are having permanent dipole. So the examples of polar molecules here. The common example for a polar molecule, say water, H2O, and say HCl, say NH3 are some of the examples of polar molecules. The dipole moment, the magnitude of dipole moment in case of polar molecules is in the order of called as permanent dipole moment. It is in the order of 10 raised to minus 29 coulomb into meter. The very interesting thing is ahead once we know about polar and non-polar molecules. The dielectric substances may be polar or may be non-polar substances or molecules here. If polar molecules is in the absence of electric field, polar molecules in the absence of electric field. Say I have a bulk material and say the material belongs to the polar material, polar substance. So when we have not applied any electric field to this bulk material, inside this bulk material, these are the dipoles, and the dipoles you can see here, they are randomly oriented. So this is plus, minus, here maybe like this. They are distributed randomly. This is the picture in bulk of a polar molecule or a polar material. Now, the net dipole moment, though the individual molecules have a dipole moment called as permanent dipole moment, in the absence of electric field, without applying an electric field to a polar substance or a polar molecules here, when we have this bulk, all these dipoles are randomly oriented. As a result, the net dipole moment in case of polar substances or polar molecules known as polar dielectric substances is 0. Though the individual molecule is having permanent dipole moment because they are randomly distributed, randomly oriented. They are not oriented or aligned in a particular direction. So the net result, net dipole moment is 0. That is, in the absence of electric field, a bulk sample or a bulk substance of polar molecules appear like this. What happens to this substance when I apply electric field? Say this is electric field. In the presence of electric field, polar molecules in the presence of electric field,